Everyone, welcome to part two of our lecture on data visualization for Data Science 1. So today we'll be talking a little bit about how we perceive visualizations and how that might influence the way that we go about trying to design them. So last time we motivated this by saying that we're trying to make human readable visualizations out of what are not very informative data tables and computer friendly data structures. And we said that the motivation for this is to tell a story with our visualization about what we want people to see in our plots, and what information we want to convey. So again, we'll be highlighting some of the ways that we think in general people tend to interpret and view plots, and how we can use that to design better ones. Again, the way that you actually go about any particular data science project depends so much on the particular data structures and type of story that you're trying to tell. But hopefully we can give some advice that will apply to a number of general scenarios here. So again, the storytelling aspect is to make things as clear and as straight to the point as we possibly can. As you may have noticed by now, one of my favorite webcomics is XKCD, and aside from being really funny, Randall has an excellent eye for creating really simple visualizations, and I think that these are inspiring in that you can immediately tell by looking at the plot what it is that you're trying to that he wants you to get out of the data that he's presenting. And for those of you who are also XKCD fans, a little side note is that in Matplotlib, one of the style plots that you can choose is an XKCD frame. I'll say that these are maybe not the best for some professional presentations, but fun for data viz on your own. So to get into what we want to talk about today, stemming from last time, is that we want to expand data visualization from being something as simple as calling a function to really being about telling a story, and we'll go from last lecture where we talked about the types of visualizations and how you might choose what sort of plot you're looking at based off of your data. Now we'll talk about the principles of how we organize and structure those visualizations, which I think will be generally informative, but also help to inform which types you choose, stemming off of last lecture. So a lot of what we're going to talk about today is how data visualization is important to communicate information to your audience or to your stakeholders. But I just want to stress before we get into that visualization is probably most immediately and most helpful to you as a data scientist in your exploratory data analysis. That so much of figuring out even what story it is that you want to tell, or what patterns you have in your data, is to be able to see what your data looks like. And one way to do that is to look at summary statistics, and Pandas has some nice describe functions built into it that will tell you that this set of data has a certain mean, a certain standard deviation. It trends along this line that you see with a particular correlation coefficient. And all of those things are helpful for figuring out what exactly your data is trying to tell you and what patterns there are underneath. But consider these four sets of data points, each of which happen to have the same exact mean, standard deviation, line of best fit, and correlation coefficient to that line. They're all within 1/1000th of the same value across all of those metrics. And so if you were to just look at those metrics, you might very easily conclude that these are sets of data from the same population that are telling essentially the same story. Yet if you were to plot each of these points, you would notice that the trends underlying them, what mechanisms you think are behind this, and what story you want to tell around this data are very different depending on which of these 4 data sets you look at. So this is a great example of how data visualization shows you things about your data that you might not see just through summary statistics. Again, as we mentioned in the exploratory data analysis lecture, just looking at your data and literally looking at it, looking at visualizations is the best thing that you can do to get an intuition about what it is that you're looking at. To expand on that with one more fun example, inspired by the previous quartet, this is the data source dozen, which similarly has to 2 digits after the decimal point, exactly the same X and Y means, standard deviations, line of best fit, and correlation coefficient. And yet you can see that there are drastically different patterns in this data, and each of which would result in very different methods and models and stories that would come out of this. So to beat a dead horse, visualize your data. So when we talk about getting into visualization, what are the best ways to actually go about visualizing, and how does human perception play a role into this? The maybe most important part of data visualization, besides thinking about kind of generally what story you want to tell, is asking how accurately you can tell that story, how much information you can get across to your audience. So just the way that our visual perception works, we are more able to resolve and make comparisons between certain types of data visualizations and others. So for example, it's really simple to tell the length of something between 2 bar plots, but it's much more difficult to guess the relative volume of 2 cubes. Similarly, we're very bad at judging the difference between 2 similar hues of color. There's lots of optical illusions that show just how context dependent we are when we're looking at color. So for example, color intensity is something that's much more helpful than color hue. Just like the length of something is more easy to accurately interpret than the angle it's at. So it's good to think about this slope as we or think about this spectrum as we think about how we want to be choosing what sort of visualizations we make. So to exemplify this, can you guess how much bigger in area the big circle is from the little one? And you can kind of do a little bit of mental math and now that they're just side by side, compare them, try and tile this over, but it's not an easy thing to do, and certainly at a very quick glance, it's hard to find a good answer. Excuse me. Tiling over this, we see that. Excuse me. Tiling over this, we see that it's the big circle is about 7 times larger than the little one. And if you were to think about the same visualization as a bar plot, hopefully it's much simpler in this case to guess about how much longer the top one is from the bottom. This is the same data that we're visualizing, so the top bar is 7 times longer, and it's much easier to make this comparison than the last one. we see this example of people perceiving length much better than area in lots of instances. That a common visual mistake, and one that I make all the time for myself, is looking at glasses that are taller versus wider, and we're on average far more likely to think that a glass contains more volume if it's taller than it's wider, simply because the width increases volume with the square of the radius, where the height is proportional to the volume. So it's again just a way to think about how our very imperfect human perception plays into how we might interpret, especially the size of some of these visualizations. So again, looking at area versus length, at least for me, it's much easier for me to compare the lengths of the plots on the top to comparing the areas on the bottom, even though once again this is the exact same data being visualized. So pie graphs are a really popular data structure for showing off proportions, but it's good to keep in mind that pie graphs, which look at angles, but also bubble plots that look at size, are nice tools to have in your back pocket. But if you're trying to convey really precise information, think about lines. Similarly, the point of area versus length is the case for squares or rectangles in addition to just circles. Even though I think circles are a little bit harder, the area here is really hard to judge. That I would not have guessed without the numbers or the caption here, that the red block for South Africa is twice the size of the green block for Algeria. Again, that we tend to look at lengths where area is a function of the square of the length. So that just messes with your perception a little bit. If you were to plot that same thing using lengths on a grid, you can see that the plot on the right, it makes it very obvious from first glance that the first row, South Africa, is about twice the size of the fourth row, Algeria, much more so than the plot on the left. Another instance where we often use areas are word plots, word clouds. Again, word clouds are great in some circumstances, but if you're actually trying to convey the relative areas, the relative frequencies, then you're much better off just using a bar plot like we have on the right. And again, this is not to say that any of the visualizations that I'm bringing up issues with are things that should never be used. Just that you should think about what story you're trying to tell. If you're just trying to enumerate the different types of words that are in a corpus, then the word cloud on the left is a nice, fun way to do that. But if the point that you're trying to get across really is about the relative frequencies, that you're trying to make a case that in this text, SQL is talked about more than R, is talked about more than Python, which is talked about more than Java, then that's something that's very much not clear to me from looking at the plot on the left, where it's obviously clear on the plot on the right. So again, storytelling plays a big part in what visualization you would choose, and vice versa. So like I said, lengths are easy to distinguish, and one of the things further down in these pie charts is the angle. So it's very hard for us to tell angles in pie charts, and also kind of absolute angles in slopes on plots that aren't labeled. And the pie chart you can get a little bit of a guess at if you visually try and ignore the pie chart and just look at the length of the circumference around the outside. But again, now you're asking your user or your reader to do a little bit more mental gymnastics here. And what you want is something that that very clearly and very minimally gets across exactly the point that you want them to draw from this data visualization. Another common perceptual difficulty is looking at uneven baselines. So you may have noticed in the spectrum of data visualizations that while lines were the easiest, it noted that harder than synchronized lines are lines that aren't matched up to each other. Looking at two lines that start from a different baseline. So, for example, in the plot on the right, the blue curves on the blue sections on the top look to be about the same length if you were to compare each of them visually. Yet, at first glance, if you look at the whole plot as one figure, the global view suggests that maybe the blue lines in the middle might be longer, just because they're higher proportionally. They're longer than all the rest, and that actually is the case that they are a little bit longer than some of the others, but that is exacerbated by the fact that they start at a higher level than the ones on the end. So this is to say that the different types of visualizations we're talking about are encodings or ways to represent information as visual elements. And length is one particular encoding that's a visual structure for a type of information. Now, if we think about encoding more generally, we can think of data going from our raw computer-friendly language into some data format that is able to be plotted. So in this case, this is the height. How many pixels, for example, above the x-axis each of these lines is plotted at. If we think about this more generally, we can think that that different encodings are better for different information structures. For example, a dot compared to a line typically has a 2D encoding because it has an x and y position, where a line either has an x or a y, but tends not to vary in the other direction since it's a one-dimensional encoding. And obviously these dots make a lot of sense in scatter plots, in which you want to show the relationship between two variables. So like we talked about last time with scatter plots versus bubble plots versus line plots, that we're able to represent different or more information depending on which visualization type we're using. So a question is, how many variables are encoded in this particular bubble plot, and maybe you can count them up. I'll give you a second. So there are four that we have. Of course, the x and y variables in our scatter plot. But also there's a variable encoded by the size of our dots, and also another variable encoded by the color. And it's good to think about what types of variables or what information you have in your data set is best encoded by which dimensions in your encoding. So in this particular example here, if we're looking at something that needs to be very precise or to compare between two nearby data points, you're much more likely to be able to resolve its x and y position than you are, like we just said, to be able to resolve the size of two different bubbles. So if that relative comparison is really important, maybe that should be one of the dimensions of your axes. Similarly here, we'll talk more about color in a minute. And the color that we see here tend to be a few discrete colors, suggesting that the information encoded by the color is some categorical feature in your data set, which makes sense to use discrete colors for, and maybe makes less sense to have along the x or y axis that are a little bit more friendly to continuous variables. So to sum this up, this is to say that that certain types of encodings are better or worse for certain types of variables. And here's an example of a plot that has a poor encoding. And can you figure out why? So the reason here is that by encoding a categorical variable along the x-axis, you're implying that the bars, which visually look longer for some nations than others, are larger, so that there's actually differences in magnitude, and also you're implying a relationship between them, that Japan is more than USA, but that Japan is less than Germany, which in this case clearly doesn't exist. And so what we would actually expect here is that some data type, which is best for categorical variables, would be used instead of the bar chart here, that implies that at least one of your dimensions is a quantitative one. So this plays a little bit into a topic from last time about which visualizations you choose. So here is a little cheat sheet. I don't completely agree with all of these, and that some of the data types suggested here, like the pie chart or the stacked bar charts, are ones that we've just said don't necessarily apply always to certain data types. But in general, the idea I want you to get from this is stemming from the center here, that where it's asking first and foremost, what do you want to show? Is it a comparison between two different types? Is it a composition? Is it a relationship or a distribution? And that's why they choose some of these plots over the others. So for example, a pie chart, while really bad for comparisons, actually is something that's reasonable for composition. It's a way to show the relative parts that make up a whole, even if you're not really able to distinguish that well the sizes of each of the parts individually, if you were to compare one against the other. So I know this is really hard to see on the video, but I'll be posting a link to this in the additional resources on Blackboard as well. So one of the things that is perhaps the most artsy of the data visualization choices you have to make is about color. And this seems like maybe primarily an aesthetic thing, but let's talk a little bit about the perception of color and how that influences the way that people will interpret the information in your visualizations. So for those of you who can or cannot see the pattern on the left, what we have is green and orange or brown points making up a number inside this circle. Yet, if we were to visualize this for someone who's colorblind, or more practically, someone who prints this out in black and white, you would not be able to distinguish what was being shown to you by this visualization. So this is one kind of extreme example of why color actually matters. So the use of color can be good to distinguish between, again, two different types of encoding, one for qualitative data and one for quantitative data. So with quantitative data, the shades and the intensity of the color can be a nice way to show a smooth transition along a continuous variable, where with categorical or qualitative data types, that don't necessarily imply an ordering, it's good to use separate discrete colors to show different discrete categories. And the visualization that we have here shows examples of both, where there's two different types of in this case flowers in the iris data set, but the features of both of these vary across the distribution of flowers within both of those subsets. Just another link to last lecture that what we have here is a three-dimensional kernel density plot. It shows the intensity of that kernel coming out of the page and the shape and size of it in the XY plane. So this is extrapolating from what we learned last time about smoothing functions to make these maps that are shown like topological maps with hills and mountains coming out of the paper. So in particular, one of the most important things to think about with your color choices is the story you're trying to tell. That even with a single quantitative piece of data here, the perception that someone brings to that data will depend on the color map that you choose. So on the left, we have an example of a single sequential piece of information where we're asking how the value grows or shrinks over time. And we can see that the color bar here shows that at one extreme, very dark values, the color is low, where at the other extreme, very high values, the color is very light. And this is also the typical ordering, by the way, where darker values are lower and lighter values are higher. Again, just the way that we perceptually think about intensity as, light is something that's very intense, where darkness it implies a very low intensity of light. And compare that sequential dark to light color map with the one on the right, where we're trying to make a statement about two diverging groups. In this case, we have a red to blue color scheme, where the neutral value, the white, is in the middle of our color bar. Into one extreme, we go towards one color, and towards the other extreme, we go towards the other color. Which is a nice way of showing a stark comparison between two groups along this same color bar. That would be much different from a sequential color bar, where people who are neutral in the middle wouldn't be represented quite so well. And you wouldn't be able to resolve the differences between the two extremes quite so well. It's also nice that with these divergent color bars, you're really encoding two pieces of information, and one is which direction you're going by which color, and the other is how far in that direction you're going with the intensity or the darkness of that color. So this is a really nice way to add information into your plot, even though you're just using a single visualization type in color. So there's been lots of work looking at different color bars, and these are some of the default color bars in Matplotlib. You can import many more than this if you're curious, but they have some standard sequential color maps. We'll talk about the top group here with perceptually uniform color maps in a second. But they have sequential color maps, divergent color maps, and also qualitative color maps that have a discrete number of choices. So to get into the perception of these color maps, here we have an example of what used to be the default color map in Matplotlib Jet, and now what is the default color map, Verdis. And so why did they make this change, and what's the difference between the two? The difference is that one's a perceptually uniform color map and one's not. So as we try and encode quantitative variables with color, one of the questions to ask is, how do changes in color lead to different perceptions in the changes in those quantities? So with the jet color map, which nicely showed a spectrum with a lot of different colors over this color map, we were constantly changing the RBG values, yet the perception of this changed in a very non-uniform way. You can see the quote-unquote perceptual deltas in subfigure A here. And I think you can pick up on these in the color map too. That, for example, in that little transition between the blue and the green, it looks like there's a very intense, very light part of light blue that looks very different from the areas around it. It almost looks like a little line in that color map that's supposed to be moving very gradually. This is maybe even more expressed if you look at the black and white version of this, where you can see those white bars as the pixel intensity changes throughout this color bar. And obviously, if you're trying to make comparisons, the comparisons between two colors along one of those stark transitions will look very different to you than transitions between some of the smooth gradations. So the new default, which is Verdus, is a perceptually uniform color map. You actually can hardly even see the plot on the left here with the perceptual delta because it's a flat line right at the top. An example actually of bad data visualization in a poor choice of AXI values. We'll get to that in a second. But you can see, hopefully you can see a pretty gradual transition across this on the left, and especially in the black and white version, that the absolute intensity of the pixels is very smooth, as shown by the perceptual delta plot for the grayscale one as well. And hopefully you can see this in the plots too, that the transitions between each of the hills and valleys, for example, in the bottom row, which are meant to be very smooth, feel very smooth, whereas in the jet color scheme, it looks like they're very sharp transitions between what seem to be almost two categorical values rather than smooth transitions in this quantitative space. So this is just to say that thinking about what colors you use is important, and luckily in the latest version of Matplotlib, they've taken this to heart and officially changed from the classic jet color scheme to one that's a little bit more perceptually friendly. So let's talk about context in your plot. So obviously, with storytelling, context is a huge thing to think about, and there's lots of ways that we can think about putting context into a plot. So this goes from the title to the legend. This is something we haven't talked a lot about, but having a legend that tells you what your different lines mean is critically important for being able to interpret a plot. Some more subtle visualization things like ticks along the X and Y axes, or grids that connect those ticks and show how those values carry across the plot is a nice way for people to resolve, what the exact values are, or when one of your curves crosses over an important threshold. The lines, kind of what type of line you choose, a solid, a dashed, a dotted, what markers you choose, like we talked about with the bubble plots, their shape, their size, their color, all are important pieces of information. But what we're going to talk about for a second here are the wording and the labels within your figures, because that's a way for you to quite literally tell the story that you're trying to tell. So for an example here, this is a plot, and can you tell me the story that's going on behind this? I can maybe guess from the legend that it might have something to do with fields, either in industry or within school, and how something about those changes over time. Um, what you see on the right though is a really a nicely labeled plot that shows the change in the gender gap between the different fields as a percentage of bachelor's degrees that are conferred to women. Um, and even in the title, it points out some of the things that you should notice. For example, early on, exactly how small this was for all of the fields. And as you can see in the plot, how different fields change at different rates. This plot could be better. I'd like to see axes labeled as well. But I think from looking at this, you can get much more of a story that the data scientist is trying to tell you here. Just as another side note for style sheets, this is the 538 style sheet for those of you who are fans. And there's lots of other fun styles that you can look at in the Matplotlib documentation too, if that's something you're into. So to add context directly to the plots, one way to do this is with titles, of course, that tell you what you're looking at, and this can be not just what you're looking at, but what you're looking for. So if you're trying to direct the user or the reader towards some particular outcome or looking for some particular pattern, you can name what that pattern is. For example, older passengers spend more on plane tickets, rather than just describing what the data types are and data sources are, which you should be able to get just by looking at the two axes labels. So to say the title is scatter plot of price versus age, hopefully you have price on the x-axis and age on the y-axis. And so that title would be redundant, where instead you could use that information to talk about what conclusion you want the user to draw. The lines and markers are ways to draw attention towards certain types of data points, and in particular, putting labels or unique colors on particular data points that you think are really important for telling your story can be a nice way to get across information. Legends and labels as appropriate. My view is that those are almost always appropriate, so please include legends, and also as appropriate captions. So captions can be subtitles in your data that like we saw in the last plot, explain a little bit more. In more scientific work, these are often figure captions that occur below the figures. So it's good to think about what context in not just what data you're looking at, but what source and what type of reader you expect to be reading it, because they'll expect to see sometimes the same information shown in different ways or in different places in a magazine or a web page compared to in an academic journal. So to go a little bit more into the captions, again, this is a way to tell a story. My personal view is that all figures should be self-contained stories in themselves and self-contained takeaways. So even if your figure is within a big academic paper or part of a really long detailed article or blog post, it's really important, I think, to tell the user what they'll see and what you expect them to be looking for, just from looking at the figure, because often people will scan ahead and read figures before they've read the supporting text around them. So you shouldn't ever rely on a user or a reader having all of the information they need before coming to the figure. The captions can be within the text as well. They don't necessarily have to be outside of the frame. that you're able to put text into Matplotlib visualizations. In this case, labeling different police commissioners inside the text, and also labeling the mayor of New York City here, corresponding to the time along the x-axis. Gives some context about maybe what the trends are and what the causes of the different trends are over time, which again helps to imply what it is that you want the user to take out of this plot. The captions and lines can also be really helpful for resolving information that's not perfect. So for example, we've said that angles are something that could be hard to resolve just by looking at this data. And so with this scatter plot, maybe at first it seems like the trend line is generally correlating well and heading up and to the right. But if you were to add more auxiliary information through captions and through in this case a diagonal grid line that shows some important threshold, it might tell a very different story. So for example, what we see here in the median weekly earnings between men and women is that in almost every discipline, what you have is men being paid more than women, and you can see this very clearly through the example or through the reference line for equal pay. And just in case it took you a second to orient, there's two text captions here telling what the two halves of the plot mean. That the points above the line mean women are paid more, and points below the line mean that the men are paid more. And in particular, it also highlights some extreme data points. So, for example, the subset of this data, the sector where women are paid the highest proportion is wholesale retailers and buyers, wholesale retail buyers. That tell us not only one particular example, but imply to us that all of these data points are sectors of the market, rather than any of the other things that they could possibly be. It's also nice to have reference lines that show not only outcomes that you think are important, but maybe some standard baseline. So, for example, we might not know just how much deviation from that equal pay really means, but by having this dotted line for a 25% pay gap, it makes the results seem perhaps much more extreme than you would have intuitively thought. It seems like while the points are below, they're not that below the equal line, but really they are. This is quite a huge problem. And again, showing one of the other extremes is a nice way to point out one of the sectors doing the worst, financial services. So again, there's this is very hard to choose exactly what visualization you might want to show. And an example like this, where you're labeling all of the data points, is something you clearly couldn't do for everything at once, and maybe is best for certain types like online interactive graphics, compared to something that is static or printed. Just to show an example of maybe this gone astray, here's one visualization from your recommended reading that just looks very busy and scattered, and even though there's lots of text and lots of colors and grid here, it's very hard for me to tell just from looking at this quickly, even reading the top comment, what it is that I'm supposed to be drawing out of this figure. So this is again to say that more information isn't necessarily better. What you want is to be focusing in as much as you can on presenting the trend in the data that you want the user to get out of this. So really quick to talk about what sort of trends you might see in data and you might expect people to see. Um, One of the best ways to identify these trends is to look for transformations. So transformations in your data are really nice ways to visually highlight some parts of your data set or some patterns above others. So in the plot on the left here, you see that we have a distribution that's highly skewed to the right, but it's really hard to resolve what's going on within that peak where most of the data lies. And often that'll be where most of the data is where your story will be centered around. And that's not always the case. Maybe the point that you're trying to make is about the outliers and the few data points out to the right, but maybe it's not. If you do want to zoom in more on some of the lower data points, one of the things you could do is cut your axis, but another thing you could do is transform this onto a log scale that shows in maybe an easier to resolve way some of the patterns that are happening on the data. So even though the data on the right is much easier to see, it's actually not cutting off or ignoring any of the data on the left side. So for those of you who aren't familiar with log plots or logarithms, the idea here is that in short, what we're looking at is instead of absolute changes, we're looking at relative changes. So the y-axis here is a regular linear plot where each of the ticks is one more than the one before. Whereas on the x-axis, we have a log plot where each of the labeled ticks is 10 times more than the tick before. So as you can see, we are able to scale magnitude much larger. And we're still able to resolve some of the issues that we see at the smaller resolutions, which you would never be able to do if you had a linear scale that went up to 1,000, like the x-axis does. So this is again to say that the way that we perceive things is about the relative change or the relative magnitude. Much more so than the absolute. That adding 1 going from 10 to 11 is a much bigger deal than going from 1,010,000 to 1,011,000. That's a fairly insignificant change, and so a log scale looks for the relative change when deciding how much space to give to each of these plots. So this is just to say that one of the things you can do is to apply these transformations to try and find patterns in your data. We'll talk a little bit more about this in future lectures, but one of the things that we really like to see and is easy to interpret is when there's a linear scale. That a straight line is something that's very easy for us to perceptually resolve. Where, for example, curves with slightly different rates or raised to slightly different exponents are extremely hard for us to compare. The difference between a straight line and a not straight line is perceptually quite simple. So if you can apply these transformations onto your axes and get to a straight line, which is to say now you have a proportional relationship, what you can do is you can ask what transformations you had to put in to get that straight line, and thus backtrack out what sort of relationship you have between your raw variables. So here we have a pretty hard to interpret relationship between life expectancy and healthcare, but you can tell pretty quickly that from the plot on the right, the log relationship between these two variables is a straight line, so it's proportional. There are lots of these different types of relationships that we can think about, but logarithms are one of the best and easiest ways to change the shape of a curve, especially when you have smooth data that just isn't a straight line. So, for example, taking the log of one of your variables, in this case your y variable, implies an exponential relationship. We won't go into the math here, but as you can tell, it's fairly easy to backtrack that out if you were to ask to. By the way, that's not something I'm going to ask you to do. And similarly, looking at a log-log relationship tells you that there's a polynomial relationship in your raw data. One of the most common uses of this is a plot that ends up having a negative slope in the log-log space, which we call the power law distribution. So this is to say that the frequency of an occurrence of something is a log-log relationship to the size or intensity of it to the power of it. And so this is a relationship because the log-log scale looks at the relative magnitude of both of those things, and as we said, that's the way that the real world works is looking at relative relationships. All sorts of different things that you look at in natural systems or the natural world end up following a log-log scale. We'll likely come back to this if we get to do a deep dive into social networks later in the semester too. So just to sum this up, the log transformation is a really nice Swiss Army knife because it allows you to do really nice transformations and comparisons from the linear space into the log relational space. And for those of you who've come from more of a math or stats background, know that that transformations are really easy to do in the log space for any exponential relationships. That we won't again go into detail on this class, but I can tell you that in practice this is a really nice trick to have. So there are lots of different functions, and I would just encourage you to play around with these, plotting them in Matplotlib, and looking at the shapes, because getting used to seeing shapes in plots and figuring out what transformations to apply to pull those relationships out and linearize them is a really nice way to go from exploratory data analysis into model building. To wrap things up here, one of the other things we can consider is conditioning. So to close up the influence of perception on the conclusions that you want to be making, you should think about how you structure your data, and especially how you structure your visualization in a way that that you can make the comparisons very easily that you want to be making. So, for example, the way that this plot is constructed, it seems like it's quite simple to make comparisons between the different levels of education, noted both by the ordering of the data points, and somewhat their color. That it looks like the data scientist here is asking us to think about the relationships in these two subsets almost separately, about how increases in education lead to increases in earnings. But maybe it's the case, and maybe not. But likely it's the case that the conclusion that you want your reader to be drawing from this is actually about the relative differences between the different genders when it comes to education. So taking the gender income plot that we had before, and looking at it relative to different education levels, and we can perhaps do that on the left if we were to rearrange the orders and group the two, for example, high school columns together for men and women, and the two bachelor columns together for men and women. But another way we can do that is plotting them on a line plot where it's easy to make the comparisons for each of the education levels separately, but also to look for trends as we increase education levels. I'll note really quickly that one of the misleading things about the type of plot on the right is that by drawing the lines connecting these categorical variables, you're implying a quantitative relationship where one doesn't actually exist. So in that sense, that visualization is not perfect. You do want to be expressing the idea that as education increases, income increases, because it seems like that's the takeaway that they're trying to draw from this plot. But by having a continuous line, you might be implying that that halfway between less than high school and high school education leads to half the income between those two. Which isn't a data point that we're considering here. So maybe that isn't a huge deal for you. Maybe you want to use dotted lines instead of straight lines to imply that there's not actually data points there. Certainly, you shouldn't show a line plot like this without the markers on those points to imply that you have data points there and not between. But again, it depends a lot on what the data set is and the story that you're trying to make. The case of talking about scale is one that was shown in your book as well. And we mentioned the axes before this, but it's probably goes without saying, but obviously it isn't always the case that people should plot axes consistently, that these two data points we have here about abortion and cancer screening, you can see that the relative values or the absolute values of each of these have no correspondence with their y position on this plot. And this is a big no-no, as pointed out in your reading. And there's lots of different ways to go about this. I won't go into the details here because you've read about this as well. That you can look at the absolute differences on the same scale, or the relative differences in terms of percentage change. Or you could look at the proportion of the total number of procedures by each type and see how that changes, which I think nicely balances both looking at the relative change and the absolute differences between them. But all this is just to say that the conclusions that you'll draw from a visualization depend immensely on how it is that you're presenting it, and what type of plot, but also what data you present. That all of the plots we've shown so far have shown exactly the same data, and yet the conclusions that you would draw from this particular plot is maybe very different from the conclusions you would draw from each of these two plots, and certainly different from what is trying to be made in the congressional hearing that you read about here. Just to wrap things up, the last thing we'll talk about in scale is that, like we said, the transformations before can lead you to resolve certain parts of your plot more than others. Sometimes just zooming in instead of applying transformations is a similar way to show the same outcome as we saw above. When you're able to just view a subset of your data. So for example, if you were to say something about the two peaks in the plot, that would be much more likely to be a conclusion that the reader would take away in the right plot. Yet if you're talking about the outliers and the extreme examples, then you'd want to show the plot on the left. And both of these are equally valid, though, like we've said before, with transformations, if you're cutting off some of the data, make sure that you're very clear about that in your methods in your write-up that you're ignoring some of the outliers to the right. Sorry, this has been a pretty long lecture, but there are lots of important and I think really interesting parts of visualization that I hope you'll take to heart, and aren't just that I'm someone personally very interested in pop psychology. Where the way that we present data playing into the way that we as humans perceive data and perceive pictures and information really go quite a far way along the way of creating a data viz where the reader is drawing out the same conclusions that you want them to. And that sort of communication is really what's behind good data science. So hopefully some of the things we've talked about today will be helpful in doing that for you. I'll wrap it up here and see you online next time. Thanks.